Hey guys, what is up? John here from fly8mikealpha.com. Today we're going to be talking about electrical systems on the airplane, specifically this electrical diagram here, this electrical system schematic that you can find in the Pilot's Handbook of Aeronautical Knowledge from the FAA. There's a lot of fancy stuff going on here. Let's take a few minutes, go ahead, dive into it, and explain to you each and every individual part and what is happening here, how all these parts and pieces help make your airplane fly, and where the flow of electricity is going, as well as what control you have over the flow of electricity throughout this system. Bottom line, everything you need to know for your private, instrument, or commercial pilot checkride. So let's approach this from the standpoint of we're walking up to the airplane on the ramp and everything is turned off, the key is in our pocket. So the key is off and the master switch is turned off. Obviously there's electricity on board because we have a battery on board. Now, as we go through this video, as soon as we encounter a symbol that we haven't talked about, we'll go ahead and explain that symbol. So first symbol I want to explain here is this one right here. 3 little black lines means the battery is connected to ground on the negative side. Now, there's 2 ways to approach this. You can either say electricity flows from positive to negative or from negative to positive. We're not here to debate theory or anything like that. From a pure instructional standpoint and from a pilot flying the airplane standpoint, it's most important for us to understand how these things work rather than how electricity really works. So we're going to explain this from the standpoint of electricity flows from positive to negative today. What I want you to realize is this is just a wire going from the battery to the airframe itself, and that metal in the airframe, the wings, the fuselage, the engine, all that stuff, can flow electricity. All right, so whenever you see these ground symbols, it actually means the same thing as wires being connected from whatever the ground symbol is back to the negative side of the battery, because ultimately, say our clock here, that's just a wire going to the metal airframe, and then the battery has a wire going to the metal airframe, and the metal airframe becomes the connection between the two. So that is how we link our grounds together, is through the actual airframe itself. Now, what we want to really follow here to start off with is power from the positive side and what is energized with electricity when we're walking up to the airplane and nothing is turned on. Well, for anything to work, anything electronic to work, there has to be a flow of electricity. So positive has to flow to negative, or negative has to flow to positive. Bottom line is they have to be joined in some way. The connection has to be closed. So if we were to go ahead and arc this, say we take a wrench and lay it on top of the positive and negative terminals, well, we'll get a big spark. Electricity will flow. But you can see these terminals aren't touching each other, so no electricity flows. What we have to do is use a wire to join the positive somehow through an appliance, like a clock, back to ground, and then the electricity can flow through the clock, through ground, back to the side of the battery. If we don't connect that clock to ground, well, no electricity actually gets through the clock. It gets to it, but doesn't get through it. So let's take a look here. We have positive coming off the battery. This jumps over this wire. That's what that little U-shaped thing there is, that little half circle. If it was just a straight 90-degree connection, that would mean the 2 wires are actually touching and connected electronically or through an actual metal connection. This is just the wire passing over the other one. So we can see positive comes here, passes over this wire, comes to this terminal on the battery contactor, also known as your main solenoid or your battery solenoid. And we can see that the electricity is going to flow upward now. And we can ignore these other things for now, where it's going to flow upward to this symbol, which is a fuse. We can come down here to our legend and see that's a fuse. Now, if the fuse is not blowing, hopefully it's not, then electricity is going to continue to flow, and it's going to hit our clock. Makes sense that we want the clock always connected to the battery, even when everything's turned off. So we have electricity flowing through the clock, making the clock work because the clock is connected to ground, thus the electricity flows to ground and back to the battery, back to the ground side there. Now, what would happen if we were to get a short, or say we disconnected the ground wire there on the clock? It would stop working. What if the fuse blew and the circuit went open? Well, no way for electricity to get to the clock now, even though it's still connected to ground. So, yep, if the fuse blows, no more clock. Where else is electricity going with the master switch turned off? Well, we have electricity coming here to our oil pressure switch, and we can see that it is open. So if we close the switch, this is the funny thing about electricity. Open means no connection, no flow of electricity. Closed means connected circuit. So this is an open circuit. This would be a closed circuit. That circuit's connected by a wire. The circuit is open. The switch is open right now because there's no oil pressure in the engine. Engine's not running. Once the engine runs, well, then that switch would close. That would allow electricity to flow through here to our Hobbs meter, our flight hour recorder, and then electricity flows through it to ground, back to the battery to ground, and that's going to make the Hobbs meter start working. Go ahead and snip that wire to ground or have this switch fail, and yeah, the Hobbs meter won't work and your flight will be a lot less expensive. Now, if you have a sticky oil pressure switch, even with the engine turned off, even with the master switch turned off, if that thing sticks, or for some reason there's still oil pressure in the engine, go ahead and blow into the dipstick tube really hard and make some oil pressure. Close that switch, well then the Hobbs meter will start ticking away and billing you and draining your account at the flight school. Now, where else is electricity getting to with the master switch still in the off position? Well, we can see that electricity comes through here to this terminal, and it also flows through a coil of wire that's inside this solenoid and comes out to this terminal. Now, what's up with this little arrow here? Well, we can see the electricity is going to flow over here and it's going to encounter a diode. The purpose of a diode is to stop electricity in one direction. So it's a one-way check valve. Electricity only flows in the direction of the arrow. It doesn't flow backwards. It's easiest if you think about electricity in the sense of plumbing or water. So if you have a one-way check valve in a water line or a sprinkler line, water only flows in one direction. So this is the same idea with a diode. Electricity can flow to here and then it stops. Electricity could also flow from this side and go through, but it can't go the other way. So anyways, we have that normal flow of electricity always on from our battery coming into this terminal, coming down into a coil of wire that's spun around here, and then coming out of this terminal, joining over, going on up over to our battery master switch. What happens when we turn on that battery master switch? Well, we'll actually close the circuit and connect that wire right here to ground, which means now electricity is flowing from the battery to ground, which means electricity is flowing through that coil of wire. Before it was there, but it wasn't moving. Now that the electricity is moving, it's going to make a magnetic field. It's going to pull down a little piece of metal inside there and connect this terminal to this terminal right here. And that is going to allow current from the battery to flow to this terminal and then to everything else and power up the rest of our airplane. Now, before we get too ahead of ourselves here, that's one way to do it. So we turned our battery master switch on, click, we hear that click of the solenoid, closing, connecting electricity from here on over to that terminal and going to the rest of the plane. Let's click, turn the battery master switch off, the right side of that master switch off, and now we're just back to this stuff here being energized. What if we want to go ahead and run our avionics or practice a little bit with our G1000 or test our radios or do something like that, run our flaps up and down, turn on all the lights on the airplane without draining our battery? Well, that's what the ground service plug receptacle is for. So that is that little thing you see on the side of your 172 where you can plug in ground power to the aircraft. You can see that when we plug in ground power, say 12 volts of ground power, we would have one side of that, the negative side, going to ground, and then we'd have the positive side coming through here, energizing all of this stuff, going right through our amp meter. And the amp meter is just a flow gauge. It's showing either flow in or flow out. So either a negative flow coming from the battery or a positive flow coming back from the alternator charging the battery. So what we would see is all of this get energized. Our primary bus comes on, our avionics bus comes on, all that stuff has electricity flowing to it now without us draining down the battery whatsoever. We also notice here that there's also a little diode that just lets a little bit of electricity, or lets electricity flow in one way. And then this guy right here, this resistor, that little squiggly line there is a resistor. That's just a constriction in the line. That's just like squeezing a garden hose. So you have a lot of water flowing from your garden hose as you're washing your car. You go ahead and kink the hose. That's what the resistor is. It lets a smaller amount of electricity flow, and then it goes through a fuse and supplies electricity to the rest of our stuff here. Now, why are we not supplying a ton of electricity through all this stuff here? Well, because we're trying to supply electricity more so just to the avionics bus and the primary bus. We don't want to supply a ton of electricity back through this circuit right here, because that would start charging up the battery, and the ground service units are not always designed to charge batteries. You can certainly use them to charge a battery, but they're not necessarily designed to do that exactly and have the right amount of flow to the battery. If you have a super dead battery, it might flow too much amperage through there, so that's why we have that little resistor there. Now, if you want to go ahead and close that circuit and allow electricity to flow from this terminal right from your ground power unit back to the battery unrestricted and charge it up, you would go ahead and flip on the battery side of the battery or of the master switch, and that would close the circuit in the battery contactor, close or create that magnetic field, closing that circuit right there, allowing electricity to flow back unrestricted through this guy. This allows a lot of current to flow. That's the purpose of a solenoid. Why even have the solenoid? Why not just run all this stuff right through the switch? Because the switch would be huge and massive and expensive. So what we do instead is we can use this little teeny switch that flows a little teeny amount of electricity, just a little bit right through there. And that little bit of electricity creates just enough electromagnetic field to actually close the circuit and allow a large amount of electricity to flow, a large current, to the rest of our electronics. The purpose of a solenoid or a relay, as you might hear them referred to, would be to control a large current with a small current, to control a large flow with a small flow. That's the idea here. Now, what happens with the other side of the master switch, the alternator side? Well, if I go ahead and supply power to that, so flipping on the right side, I get power to all this cool stuff over here, but I'm going to show a negative amperage draw because I have electricity flowing this direction, and I've got power to my beacon, my pitot heat, my strobe lights, and I got my power to all my radios and all that cool stuff. It's all great, but I want to make some power now. Well, let's assume we get the engine running. Then we would have the other side of the alternator, the other side of the master switch turned on, the alternator side. And what is that doing? Well, that actually takes electricity and supplies electricity to the alternator. So this is an open circuit here right now. Where are we going to get the electricity from? Well, we have electricity that's going to be flowing from the primary bus back through all this stuff here, and then eventually working its way to power in to the alternator control unit, or a voltage regulator as you hear it referred to. And we're going to supply power to the alternator, to that F terminal there, and it's going to go ahead and make power and put out more power. We have a circuit breaker here that's going to control power to the alternator field itself. So when we flip on that switch, when we close this circuit, we could actually cut off flow of electricity to the alternator field via this circuit breaker right here. But as we supply power to that alternator, it's then going to put power back out through here, flowing through our alternator circuit breaker back to our primary bus, supplying electricity to the primary bus, also supplying electricity to the avionics bus, and also supplying electricity back the other direction through this ammeter. Now we're going to show a positive charge, and it's going to come back through here to our battery contactor, which is closed, which allows electricity to flow back to the battery and charge the battery. So that is if the engine's on, but hold on a second here. How do we get the engine running in the first place? Well, that is where our magnetos, our ignition switch, and our starter contactor or starter solenoid all come into play. So we also have electricity that's going to be flowing once we turn the right side of the battery master switch on. So we have electricity now flowing from the battery to this terminal. It's also going to be flowing right to that terminal. So, okay, we have 12 volts now when we turn the master switch to on. We have 12 volts to our starter solenoid, or our starter contactor as it's labeled here on this diagram, this schematic. How do we get 12 volts to this terminal to actually supply 12 volts to the starter, right? So we need to close that gap. Well, this guy right here comes through, and it has a little coil of wire, just like the other one did. So it has a coil of wire inside there, so electricity is going to be supplied there once we have the battery master switch turned on. And that coil of wire then comes out through here, jumps on over to our ignition switch. And we can see that our ignition switch is grounded. It's grounded for a couple different reasons. But for this reason, we're going to talk about just how it's going to work the starter. When we go ahead and turn the key over to this position here, so we rotate that key, click to start, we allow electricity to flow through here back to ground, which is allowing electricity to flow all the way through the starter contactor, which creates an electromagnetic field, which closes the circuit between these two terminals and supplies a whole bunch of power from that battery on over to the starter motor. The starter motor is bolted to the engine, thus it is connected to ground, and electricity flows through the starter motor, a whole lot of electricity, back to the ground, back through the engine and the airframe, back to the battery, and that gets the engine running. Now, what else do we have going on here? We also see where we have magnetos. The purpose of having the magnetos connected to the ignition switch, it's not that we're going to ever supply power to the actual magnetos themselves. There's no 12 volts coming into the ignition switch to send it out to the magnetos. What's actually happening here is that the magnetos are going to be supplying their own power, and it's either going to jump across a spark plug gap to ground and then flow back to the battery, or they're kind of like little alternators actually. Or if it doesn't do that, what would be the easier path? Well, if we just went ahead and connected this wire to ground and allowed the electricity the magnetos generating to flow right through the ignition switch back to ground, instead of having to jump across the gap of the spark plug that's in the engine. Now, why would we do that? Well, we want the magnetos to not produce spark when the engine is not running. When we put the airplane in the hangar, we tie it down on the ramp, we don't want it to accidentally start, so we want to ground out the magnetos. So we connect, by turning this key to off, we actually connect a wire from the magneto to ground, so that if the magneto makes a spark, it goes right to ground, right back to the battery. It never goes through the spark plug itself. If we were to cut this wire, our P lead is what we call it, if we would cut that, or it broke, then we would have a hot mag, or if we left the key on both, or left or right instead of off, we could have a hot magneto, meaning that when it creates electricity, it's going to jump across the spark plug gap rather than travel through the ignition switch and back to ground when it makes that spark. Now, that is the overall system here, and there's a few little things happening up here that aren't depicted so well in the alternator control unit, as far as when we get low voltage from the alternator, how we're going to have power to this light bulb here showing us, hey, we have low voltage warning light for our alternator. We also have this that's going to go to a circuit breaker that's not really depicted here, to the instrument light circuit breaker back on the other side of this diagram here. All these other things here, once we supply power to the primary bus, that's just a big strip of metal that we then have circuit breakers mounted to, and the electricity flows through the circuit breaker, say for like our landing light, for example. So once we turn the master on, we get electricity flowing on over here. We hit the primary bus with electricity. It comes through the circuit breaker, which is closed. This would be an open circuit breaker. It's popped. This one's closed. It's working normally, and it allows electricity to flow to the landing light. It flows through the landing light bulb itself and then back to ground. So you'll have a wire that runs all the way, theoretically, you could say there's a wire that goes all the way from the battery through all this stuff here to the primary bus, to the landing light circuit breaker, to the landing light switch, to the landing light itself, and then the wire for the ground. So you have two wires, one going in, one going out of the landing light. Where's the wire going out go? It just gets screwed just a few inches away into the actual wing itself, which is metal, or some sort of metal piece in the wing if you have a fabric wing. And that grounds out the light, closes the circuit, connects everything back to ground. So we don't have two wires running full length all the way throughout the airplane for every piece of electronic equipment that's in our aircraft. We typically only have one wire, a positive wire, going out to a piece of equipment like a nav light, and then that nav light is simply grounded to the airframe, just like we have one positive wire coming in here to the starter, and then the ground wire is only an inch or two long, or in the case of the starter, there is no ground wire. It's just bolted right to the engine, which is ground. In the case of the clock, there's probably just a 1 or 2 or 3 inch wire coming off of the back of that clock, going right to ground, somewhere on the airframe to ground it out. That's how that stuff works. So we can actually save weight and save materials when we're building airplanes in that sense. Something that this diagram is leaving out is, of course, all the switches. So we can see we have landing lights here, we have strobe lights here, but we don't actually have the strobe light switch, and we don't actually have the strobe lights themselves depicted here. But ultimately, that is the depiction, say, for landing lights and taxi lights. Say if we had landing lights and a taxi light, that's how it would look. Perhaps we have a 2-position switch where we have one, the other, and then both. Perhaps we have 2 individual switches. That's how that stuff would work there. That is the overall electrical system schematic. That's what the FAA is trying to depict here to you with this diagram, just with, well, in their book, a little bit less explanation. So hopefully this video was helpful. If you have any questions on this stuff at all, certainly leave your question in the comments below. We'll get more into electrical theory in a separate video because there is a lot to talk about in the sense of electrical theory, why we use resistors, why we don't use resistors, why we use diodes, things like that, and how we can calculate electrical flow, why we use thick wires some places, thin wires other places. But ultimately, if you want the simple version to try to wrap your head around this, it's just like water. If you need to flow a lot of water, you need a big old hose and a lot of pressure. If your pressure's fixed and voltage is pressure, so we're always at 12 volts or 14 volts on an airplane, or 28 volts, whatever it's set to, whatever that airplane's designed to be. So our pressure's always set. So if we want to flow more electricity, we're going to need a bigger hose. If you need to flow more water, you need a big hose, just like the firefighters. If you're just watering your grass, you need a skinnier hose. If you're drinking a milkshake, you need an even skinnier hose, a little straw. So when we have little bits of electricity flowing, like through magnetos, little bits of electricity flowing for a clock, skinny wires makes sense. When we're flowing lots of electricity to a starter motor to get our big old engine started up, well, we need a big hose, a big, thick, heavy wire. That is it for the electrical system schematic video here, guys. I'm done talking. Like we said, any questions on this stuff, comments right below, or go to fly@mikealpha.com and click on the Ask a Question button at the top of the page there so one of our CFIs can directly address your question via email or via phone for you. We are here for you guys 7 days a week to help you out with your private, instrument, commercial, CFI, tailwheel, seaplane, you name it, anything you are doing in aviation. We have awesome online courses for you on our website at fly@mikealpha.com. Full ground schools, written prep courses, Checkride prep courses, all that good stuff for all the different ratings out there. Whatever we can do to help you out with your aviation goals, certainly let us know. And if you cannot fly every day, then fly8mikealpha.com, and we will see y'all in the next one.